Assalamu alaikum. My name is Haris Ali. I'm design and fabrication specialist at Revive Medical Technologies. Today I will be conducting the first knowledge transfer session being held at RMT. The topic for this session is applications of 3D printing in medical industry.
What is 3D printing? 3D printing is an additive manufacturing process. What is additive manufacturing? Basically, additive manufacturing को अगर हम simplify करने की कोशिश करें तो it is हम दो तरीके से चीज़ों को manufacture कर सकते हैं. One is कि either हम चीज़ों को build करके bricks की तरह construct करके तैयार करें या दूसरा है if we उनको remove करके एक shape बनाने की कोशिश करें. तो 3D printing is an additive manufacturing process जिसमें हम build करते हैं चीज़ों को ऊपर add करके. So हम what we do is we use computer aided technology design 3D designing को use करके we employ that and we create 3D objects using different methodologies. So that is 3D printing in a summarized form. Okay, so just that video was just to give some visual representation on what this thing is. There are much other technologies that are employed in this as well. This was just to give a basic idea about how 3D printing looks like and the basic impression of it. So I'll start with the history of the 3D printing a bit, because Ahmad had requested me specifically to give a bit of a background about how this technology came into place. So there is a bit of a controversy, or you can say an argument on who started what. But basically, what I found was that Mr. Hideo Kodama, he's a Japanese scientist. He's the first person who started working in 1970s on this principle of curing, UV curing layers and creating objects from 3D objects on that. So he was working on this concept. He couldn't patent it originally. There were other people who got the patent before, but he was one of the first investigators who did it. So Mr. Chuck Hall is the person who everybody calls is the father of 3D printing, because he did the same thing that Hideo Kodama did, but his theories were a bit more refined, and he actually practically tested them and he got results out of them. He published the first patent for lithography, uh, and in 1983, and he later on he was also beat to the patent for it. There were these two French scientists who actually got the first patent for the technology, but he was the first person to do it, but he was a bit behind in the patent run. He established one of the first commercial 3D prototyping company in 1986, 3D Systems. You can Google them. They're one of the biggest 3D printing commercial manufacturers for 3D printing technologies and 3D printing services. They made the first commercial SLA printer. I will later on explain what an SLA is. It is called SLA1. They made that in 1987, and but this was not the first printer that was made. There were other people who actually formalized the technology in between that. But he was the first person to establish a commercial printer that was available to the market. Mind you, that at this time, 3D printing technology was very, very expensive, and these printers costed somewhere around $300,000 at that period. It amounts to somewhere around $600,000 or $650,000 at this point in terms of currency depreciation, if you look at it. After that, his one of the biggest uh, inputs that he gave, contributions that he gave us was he created the STL file. He was one of the principal persons in developing the STL format, which is used in understanding 3D printing and then attributing that into a design model, into slicing it, and then making 3D objects out of that. The first 3D printer was made by Bill Masters. This was like a drop on demand type technology that he actually made. And his explanation is a bit weird, but he was actually a person who was actually working. He's one of the first people who had actually developed kayaking. He made the first kayak, and he established that kayaking concept commercially, that people started doing it. He established one of the first companies for that. His explanation is a bit weird, but he says that if you shoot a spitball down and it sticks, you can shoot multiple down on it, and they can stick and stick and stick, and until eventually you can build something on it. So a spitball is, अगर स्कूल में आप लोगों को याद होगा कि वो उसके स्ट्रॉ में डाल के आप वो पेंसिल का बॉल बना के फेंकते थे और वो जाता था, तो उसकी एक्सप्लेनेशन ये थी कि वो स्टैकअप होते जाएंगे तो आपका 3D प्रिंटर बन जाएगा, 3D प्रिंटेड ऑब्जेक्ट एक बन जाएगा. तो उसने उस कॉन्सेप्ट पे ये कायाकिंग करते हुए पानी के अंदर, ही वाज सिटिंग इन अ लेक फिशिंग, एंड ही गॉट दिस आइडिया. आई नो हाउ ही गॉट दैट आइडिया, बट ही गॉट दैट आइडिया, एंड देन ही वेंट ऑन टू बिल्ड दिस machine, and he got it patented in 1984. Then comes Carl Deckard. Now he's another guy. There were two of these people, but he was one of the main inventors of the stereo selective laser sintering process. This is another type of process that Mr. Carl Deckard established in 1980s. I couldn't exactly find the exact date for this when he actually got it patented, but he was the first persons to get it done. And he established one of the very pioneering companies in 3D printing called Desktop Manufacturing, and they also made commercial printers and provided services. And later on, they were the biggest competitors to 3D systems at that time. But eventually, 3D systems became so big that they actually engulfed them in 2001, and they had to sell it off. Now comes Scott Crump. Mr. Scott Crump is one of the most important persons that in this whole endeavor, because he established FDM printing, fused deposition modeling, in 1988, and he established this company called Stratus, because they provide the biggest manufacturing 3D manufacturing services in USA and all around the world, and they have been very notable in enhancing this technology specifically, and they've moved on to other technologies now as well, but they are very common, and you can find their names in a lot of NASA related projects and other aerospace and Boeing and those companies. We're working with them. They've got a very massive industry in which they do large scale manufacturing. So they're one of the biggest companies in that essence in providing services. Okay, now we come up to in 1993. So SolidScape, previously known as Sanders Prototype, they established the first inkjet 3D printing. They were the people who actually modified that technology and got it in, and then they developed inkjet printing on it. And they established the dot on dot technique for 3D inkjet 3D printing. Later on, selective laser melting. This is also called DSLM, direct laser sintering method. It was developed by this Frohofer Society. I think this was German. They established this technique in 1995. In 2009, the FTM printing technology printing patent expired. So now, accordingly, after that, a race sort of began after that, that all the Chinese and all the American companies tried to get this technology and make it more cost effective and user friendly. So at that time, this RepRap movement began. And in this RepRap movement, what the concept was that they used a commercial printer to build parts for a small printer and a tabletop version, and they ensured that from that tabletop version they will build another, and then they will build another and another, and that's how the process began. Because of that aspect, what happened was that all the design files and the concepts got open sourced and got available to all the people to replicate. And accordingly, Chinese were one of the very were first to actually started copying these concepts, and they developed desktop cost-effective printers. One of the very popular companies are Tech and Creality. There's a Tech printer actually lying down there. Dr. Murza procured it. That is also one of the first generation printers that actually they built for in China. And afterwards, a lot of companies came in and made the cost. And now the 3D printer, which used to cost $300+ at that time, it costs less than $100 even. There are options available for $50, $60, $100 for that. In 2020 onwards, since this technology became very cost effective, even the higher generation equipment became cheaper, and all the materials and resources available for them started becoming very commonly available. So companies like Airbus, they started inducting these equipment in their development processes and prototyping especially. So they started this project called Build an Airplane in 2010, and they developed a concept airplane fully 3D printed, and they flew it and they tested it. It was a very popular concept at that time. Okay, so I'm going to refer to some of the common types of 3D printers that we are using these days. So first is resin printing. It has further divisions in SLA, DLP, LCD. I will later on explain about these. Then comes selective laser sintering, SLS. Then comes fuse deposition modeling, FDM. Then is direct metal laser sintering, DMLS, and then electron beam melting, and then polyjet printing. I will give a brief sort of description about these equipments and some visual aid to get you an understanding about this technology. So before I start with resin printing, I would like to explain a bit about photopolymerization. Although I'm not a materials person, but I'll try to be as concise and as accurate as possible. Okay, so photopolymerization is a material that changes properties when exposed to light, often UV और विजिबल रीजन ऑफ इलेक्ट्रोमैग्नेटिक स्पेक्ट्रम. इसको सिंप्लीफाई तरीके से अगर मैं बताऊं तो अगर आपने कभी बाजार में जाते हैं तो आपने देखे होंगे उनके ऊपर वो जिल्द लगाते हैं फ़ोन के ऊपर या ऊपर वो केसिंग्स आपकी लगती हैं तो उनके ऊपर वो यूवी क्योरिंग करते हैं तो उसकी वजह से वो स्टिक कर जाती हैं. तो ये फोटो पॉलीमराइजेशन एक टेक्निक होती है. इसमें पॉलीमर्स जो होते हैं उनके अंदर बॉन्डिंग होती है, उनकी जो स्ट्रक्चरिंग स्पेशली स्ट्रक्चरल उनकी जो बॉन्डिंग होती है वो स्ट्रेंथन हो जाती है, हार्डनिंग हो जाती है. इस वजह से वो यूटिलाइज किए जा सकते हैं फर्दर. तो ये एक कॉन्सेप्ट जो है फोटो पॉलीमराइजेशन का, इसको स्पेसिफिकली एम्प्लॉय किया गया रेजन प्रिंटिंग में, जिसको ओरिजिनली चक हॉल और उनने उसने हिडियो कोडामा ने इसको एक्सप्लॉयट किया था कॉन्सेप्ट को. इस कॉन्सेप्ट को 1950s में इस कॉन्सेप्ट के ऊपर काम शुरू हुआ हुआ था, बट 1970s में इस कॉन्सेप्ट के ऊपर ज़्यादा वर्किंग की गई है. एंड इसमें बेसिकली जेनेरिकली जो 3D प्रिंटिंग होती है उसमें ये जो है बेसिकली जो normal photopolymerization होती है उसके अंदर you have initiators and a lot of other additives as well that expedite that process. Okay, now I'm coming to resin 3D printing. What is resin 3D printing and how this technology is being used? We also have a resin 3D printer technology at our end. So just to give a brief layout of what resin 3D printing is, basically it is an automated machine which has a bath which is called a vat, which is placed onto a base which has a laser or UV projection system underneath it. And over on top of it, it has a built platform, also called a build plate, which is attached to a computer controlled actuation system. This concept actually works. There are three primary types of 3D printing that are actually done in technologies that are employed in resin 3D printing. The first is SLA, stereolithography, which was one of the original concepts that was established. This actually involves a laser beam that is angled by a specific mirror or a prism type device that angles it on top of the build plate, which has the liquid poured inside it. And it creates a layer by layer diagram, layer by layer cured layers on top of each other. And the layers slowly start moving up, 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 up. And one layer is prepared, then the next layer is prepared, then it moves up, and then the next layer is prepared. And the whole object is sort of prepared underneath that. So that is the concept of laser curing. This wasn't a very expensive technology originally. The concept was very difficult to execute as well. There were very selective companies. Formlabs is one of the very popular companies these days. They made their SLAs, but this technology needed to be made more cost effective. So in came LCD 3D printers. These what they did in this was that rather than using a laser to move it, they placed a whole LCD underneath the bath, and the design on that layer by layer design was sort of the LCD would light up in the way the design was, and it would layer by layer cure the design, and the same principle would happen. The third technology that came into place was direct light processing. In this, they added a projector, and the projector would move, the light source would remain fixed, and the projector would move, and that would angle in the light. All three technologies have their advantages and disadvantages primarily, but LCD is the most cost effective out of the two. SLA is the most accurate out of the two, and DLP is the most cost effective in terms of usability. It has a much longer lifespan, less reusable parts. Because in LCD, you sort of have to get the LCD replaced after a while. Laser itself is very expensive, so DLP is a very cost effective solution in terms of the machine. The equipment is more reliable and can run. So these are a couple of medical devices that have been printed from different resin printing technologies. You can see there's a laryngoscope, a mask, and some connectors, syringes, and stuff like that. These are transparent, but you get opaque materials as well. You get flexible materials as well. There are a lot of different types of them using different materials. This is our 3D printer that we are using. It does say 70 millimeters an hour, that is 7 centimeters an hour. That is the production speed for this. But I have seen works where it can go up to 15 centimeters an hour. You sort of have to reduce the overall quality, but you can get 15 centimeters of height printed an hour. In SLA technology, the biggest advantage is that you're playing layer wise. So if you're printing an object, if you print multiple objects simultaneously, although it will use more material, the time will remain the same. Overall, if you print 10 objects together which are in the same line, it will print all 10 objects in the same time. Only thing that differentiates the time is the height. So the taller the item is, the more time it takes to cure and more time it will take to produce. So in mass production, if you look at producing more parts, this is the technique to go for. Even SLA and SLS both are the go-to methods for mass producing parts. Here is just an image for 8K and 4K resolution, just to let you guys know that how advanced 8K is. There are 12K resolution printers now as well. They are very expensive, but they go to that depth and they touch somewhere around 15 to 12 microns of resolution in that. But we are at 8K and it is pretty good in my opinion as well. Okay, now I'm coming to selective laser sintering. Now this is another technique that is employed. Now over here, we previously worked with the part being printed from the bottom, and it was linearly actuating upwards. Now laser SLS is primarily done from the top, and there's like a powder sort of a material that is underneath. Okay, so you've seen the now we are playing with powders. Before we were playing with liquids. Now we have powders over here. So in the just in the selective laser sintering process, we've got powders. One there is a main bed in which the laser is curing the material, and layer by layer there's a roller that removes the excess material from top of it and then adds more material over it as well. And layer by layer the platform moves down and you start getting the 3D print made layer by layer downwards. You saw it in the video as well. So this is another effective process. Afterwards, once this is done, you have this whole big powdered bed, and you take that bed out and you have to remove all the powder, and the part is underneath it. The part is very neat. It has a very good resolution overall, but it still needs a lot of fine finishing afterwards. It has these resin type particles printed on top of it, and you have to do a lot of post process finishing to get a really finished product out of this concept. But again, it is very cost effective in terms of mass production. If you look at it, you print a lot of complex materials on it, nylons and Teflon and stuff like that. There are a lot of complex materials that are used in this technology. Next is FDM 3D printing, the most commonly used 3D printing, drop on demand 3D printing. There are a lot of terms used for this. In this, there is a nozzle, and there's a heated bed that is used to print the model, which can either move or which can be fixed, and the nozzle can either move on top of it, or the bed moves and the nozzle moves in either two dimensions, X or Y. And then the nozzle has a feeding system that is from and a direct feeding system that can be either placed on top of the nozzle, or would have an external feeder that would feed a filament type material into the nozzle, and the nozzle would be heated, and it would heat up the material and it would extrude it out. And the extruded material would be placed in a specific design as per your drawing, and that had, as per your 3D design, that had been sliced and put inside this 3D printer, programmed inside this 3D printer. It will print it layer by layer and will move up slowly, slowly. Now, over here, you can have single nozzles, multiple nozzles, which can be used to make different types of structures. But there are a lot of limitations in this 3D printing processes, especially overhanging. When we're making an object and it is overhanging at some point, and if there's no support underneath it, it will just fall down. So we need to add a lot of supports in this process. And when we're building it, you have to be very careful about what type of design you're printing in it and what sort of orientation you put it in. There are a lot of limitations in the previous ones as well, but this has the most amount of limitations in terms of processing. But the main advantage is that the material itself is very cost effective, and the process itself is the machine itself is very easy to build. It is a very simple computer controlled system, and there are a lot of options available that are from cheaper to very high end. And the overall difference between a high end printer and a normal printer is just consistency. The resolution part is primarily generally the same overall. If you just change the speed, you can get the same quality on a very bad printer. On a very cheap printer, you can compare that quality with a very expensive printer as well. It is just about speed at the end of the day in this technology. Now, this printer is a very unique printer because the original story behind this printer was that this was a startup project that started, and they weren't supposed to be a startup. They were kind of like our company, Dr. Murza. And in this, what they did was that they had all the funding available with them. And what they did was they built like hundreds of these devices, and they sent all these devices free of cost to all around the world, to all these reviewers and big short companies, and they told them to test this printer with every single printer that they have, and they said that it will compete with the best of the best in the world. And this printer proved to them that it could go up to 400 millimeters per second speed, which was, how should I call it, obnoxiously fast for 3D printing, because 3D printing is usually done at 60 mm, 70 mm, 80 mm. That is like a good speed. But 400 mm is too fast. Only the big companies like Stratasys, they can make those 3D printers, and they are very, very expensive. They cost in millions of dollars to get that level of accuracy. So they built that printer. It has LiDARs inside it to level the bed. It keeps on correcting itself. If there is some sort of layer variation, filament variation, it collects. It has sensors on top. It extrudes 4 filaments at one time. You can go up to 16 with it. But the biggest advantage in is that it differs from other printers because it has a system in which it can change the filament simultaneously running. Whereas other 3D printers, they have a different system in which they remove the filament and they place the other one. This doesn't do that. This can just keep on working on it and simultaneously insert the other filament while extruding it. And what happens is that it is so smart that it has what you call it, an extraction system outside, that when it's changing the layer, it sucks a bit of excess material and it prints the 3D print with that for that time being, and the mixing material is sucked out while it is using that material, and it throws it out. So when this printer comes, you'll see a lot, when we're doing mixed printing, you will see a lot of debris coming out from the back. That is all the mixed filament that is coming out. So it ensures that you don't get mixed color printing. That is one of the biggest qualities of this 3D printer. And along with that, when it starts injecting that, it ensures that if you're printing multiple materials, like one is a flexible material, another is a hard material, or one is a washable material, what it does is it knows the properties for it. So it changes the temperature settings of the 3D printer and the speed according to that as well. So if you're printing supports, it will manage it in a different way. If you're printing washable or flexible printers, it is doing it in that different way. So you get multi-structural printing done with multiple materials with this 3D printer. It does have its own kinks. We've already noted down all the issues that it may have, and we will put up those issues to Dr. Murza as well, because we will have to get some parts for it later on, which will eventually get, which will deteriorate after a while, in about 6 months or a year, and we will have to replace those parts. They're not very expensive parts. The biggest thing about this company was because it started as a giant in the beginning. It sent those pre-printers and got. They have the cheapest aftermarket parts in the world. There is no 3D printing company that gives the cheapest. I'll give you an example. The nozzle that they have, Dr. Murza, the full nozzle, assembled nozzle with extrusion is only $14. And the cheapest nozzle, he knows it. He's seen fully assembled nozzle with everything, extrusion and everything inside it, costs more than $30. So that's how cheap they are. Again, the principle is similar to SLS, but now we've got metals over here, which are being melted and bonded together. And you can see it has very fine sort of parts coming out, very strong parts, but again, they require a lot of finishing. Sandblasting is one of the very critical processes that come. So usually most of the machines that come that you buy, they have the sandblasting system already integrated inside it because you don't get finished parts properly. And sandblasting is the only way you can go inside those small crevices and stuff. And later on, you have to go into electro polishing and stuff to get that sort of finishing out of these parts. So again, same principle as SLS, slightly more refined mechanism because it's got metal in it. The powder is ensured to be very, very refined. The more refined the powder is, the more small the granules are, the better it does. If the weight of the granules is increased, the parts start failing. So they have to ensure there is a specific size of granule that is used in it. If you increase the size, then it sort of fails later on. So that is but there are a lot of issues in this process as well. Here, PAPRs come in place. Without PAPRs, they are not recommended to be used because the dust is so toxic that breathing it in is very, very, and there's been a lot of cases when people use this technology and they had a lot of critical issues coming in, metal poisoning and stuff like that. So PAPRs are a must when using these devices, and a lot of companies use those in this technology specifically. So what they are doing is, I'll explain it in the next video as well. So they developed a 3D printer that employs two principles of creating a 3D print. So they created a printer in which they are using FDM based style wire filament spools. The wires are like aluminum, stainless steel, and stuff like that. And they've got a spool holder in the back. And what they've done is that the wire is coming out, and there's a extrusion system inside the machine. And there's a laser that is simultaneously welding the wire in forms of beads, and it's putting the wire over there. And simultaneously, a pulse arc welding system also integrated inside it that is merging the two layers between, and that is their principle. So they've used two different type of technologies: laser, FDM, and the third is pulse arc welding, and they've created these hybrid technologies. This is their unique concept that they developed, and they can produce pounds of metal that they can make. They made their first rocket in under 60 days, fully functional, fuselage, shell, everything. So just to give you guys that the world is going very fast, and 3D printing technology is 100% the next generation now. There is no question of that. They just need to make this concept a bit more cost effective. That's all. And I'm pretty sure somebody will find a solution for that as well. Okay, next comes electron beam melting 3D printing. I wasn't personally familiarized with this concept, but I read it up and I started to understand it. This is another type of technology where you, instead of using a laser, they're using electron beam welding. So an electron beam is a controlled stream of negatively charged electrons that are propelled at a high rate of speed. Metal powders can be consolidated into a solid mass using an electron beam heat source. Same principle, they can melt the metal with by directing the electron beam on them. It will heat the metal up and it will melt and weld. Similar principle. The parts are manufactured by melting powder layer by layer with an electron beam in a high vacuum. So vacuum comes in place in this. You cannot do it in a normal place. So it needs definitely needs vacuum element over here. The metal parts are dense and retain attributes of the target material. The beauty about this technology is that you can use very heavy powders. Whereas in direct metal laser sintering, you saw that I clarified that you couldn't use very heavy particles. You had to have a very specific size of metal grains. So you can use very heavy particles in that, and they can retain most of their metallic properties in this as compared to laser welding. Laser welding sort of distorts the materialistic properties as well, and they have to be later on uh, annealed, heat treated to get their sort of more refined metal properties back. Okay, here's a video of one of the machine systems. Arcam, again, very big company that builds these. Similar process again, just in vacuum conditions. So this is a bit more faster than lasers again. And the parts are a bit more refined as well. It has less of the granulated aspect as compared to those metal laser centric. Okay. So next is polyjet printing. Again, it was a first for me. I saw it. It is kind of similar than other everybody else. I think this is inkjet printing category that comes in. It has multiple nozzles that eject material out of them, and they have computer aided programming in which each nozzle can work in a different manner. It may have syringes attached to them. It may have pumps attached to them. There are multiple concepts in this, and these are used in a lot of industries. Mostly, the recent one I saw was in uh, drug pharmaceuticals. They are using this technology a lot to prepare specialized dosage, customized dosage elements. I'll explain later on about these. Okay, re-highlighting again. Jet-based system protrudes out the material, plastic, probably in form of resin, which is extruded out. It also has UV curing aspects there available, which cures the layer by layer, and you can get sort of multi-material sort of concepts prepared with this system, this technology. Okay, now coming to the main topic, that is 3D printing medical applications. So there are a lot of applications for 3D printing in medical, but I try to dial them down into some of the main categories that are used. So medical device prototyping, that is definitely one of the first things that this technology was used for. Then comes bioprosthesis and orthopedic supports. Then is anatomical models for surgical procedures. Then bioprinting tissues and potentially organs, customized drug dosing and drug delivery devices, customized implants. And there's still a lot of more sites that they are being used in medical industries for, but these are some of the ones that I've worked on. Okay, so 3D printing prototyping. Now, this is a big sort of a domain that 3D printers are being used in. Different printers are used for different applications here. You can see a couple of concepts that are over here. There's a laryngoscope, there's a bone, skull bone implant over here. There's a foot model, there's a screws and nuts and those concepts as well, which can be modeled from this concept. So the main thing is that it is the go-to technology that is being used for any sort of prototyping technology. You make a prototype first using any of these 3D printing technologies, and then afterwards you can replicate that technology using some other material or a mass production sort of concept. You can validate or verify if that overall design concept is viable or usable. So that is how it works in prototyping. Now, after you prepare a prototype, there are certain techniques that are employed to make it more usable or more realistic in application in terms of even prototyping. So what people do is that there's this method called lost material casting. It is usually highlighted as lost PLA casting. In this, they usually 3D print using FDM printers. They use PLA type materials. That is one of the most cost effective materials. They make parts out of that. They make a mold out of it, and then the mold is usually like a sand mold or something. They put the part inside the mold. They They put the mold the part inside a sand mold. They split it up. They remove the part, or they keep it inside it, and they pour hot metal or any other liquid inside it, which cures. And afterwards, you get a part like that, the aluminum part that you can see out of it. It is again very rough because you're using sand and stuff like that. But if you use specialized molds like silicone and other molds, it can definitely manage much better. People usually use ceramic molding in this case to get a much more refined output out of it. There's a probability that light may go, but I'll try to quickly finish it. Okay, injection molding is another thing. Resin printers can be used to prepare injection molded injection molds for injection molding, which can be used to make plastic parts. Now, recently they have even developed metallic molds, which can be used to make metal parts as well, and even some ceramic type parts as well. So this is another application for that. This is one of the Dr. Mirza available small scale injection molders, tabletop molders that you can get, and you can make small scale parts with these. These are not the very expensive. I think they are very cost effective in terms of procurement. Electroplating is another concept that is used to get a much more refined and much more solid part. Here you can say this is copper plating actually that's being done, and you've got a bath that has copper sulfate solution in it. It has two copper plates that acts as the electrode, and your part is placed inside it. I worked a lot on this technique, and you have to sort of coat a conductive layer on top of it. And once you have that conductive layer and it has a specific type of level of resistance on it, you have to file it and get a very smooth sort of finish before you place it inside. You can then conduct the electroplating process in which the metal goes and it gets coated on top of the product, and you get this sort of finish. You can actually get this finish in the first go as well if your process is very optimized. This is very good for aesthetic, and it adds a lot of strength to the part as well. Copper definitely is not the best material to use because it has some non-biological, it has some elements that is not very good friendly for human aspects, but there are other concepts that can be used to get a much better sort of output from this as well. Okay, so bioprosthesis and orthopedic supports. So these are just a couple of concepts of bioprosthesis. These been done a lot. Everybody has done them. Nothing's very special about it. But the only thing is refinement. People are going towards refining these things. This is this lady that is gripping this bow and arrow, which is also 3D printed. If you look at it, she has a fully automated prosthetic arm, which actually works with her brain. She actually can stimulate it using her own nervous system. So this is one of the working concepts for this. Bioprosthesis. Another thing is orthopedic supports. Here is one of the supports, a cast support, or should you call it, armband type support concept that has been 3D printed. They X-rayed the arm, they saw the whole design on it, and they made a customized uh, orthopedic support. They've done this for leg supports and limbs and stuff, and a lot of other parts are being done for this as well. Now comes anatomical models for surgeries. So doctors not in Pakistan but abroad, a lot of doctors they deal with very complicated cases. So they look to teach their students, and they look for options to evaluate the conditions of the patients. So they can get CT scans and 3D scans done to mimic the anatomical model in a 3D form, and then they can get those parts, those elements 3D printed, and then they can teach them, use them to teach students and stuff like that. You can see there's a heart over there, and they're conducting an open heart sort of surgery on it. They used some flexible materials to make, which had similar properties to heart structure, not exactly, but something similar. And they can teach students and stuff as well. And then they can even evaluate issues as well, or they can demonstrate them. Now comes bioprinting tissues and organs. Although this is Hassan's domain, but I just went through it to understand it and give you a bit of a brief on it. So uh, basically, bioprinting was developed or is being considered primarily as replacement for tissues or organs. The technology is not yet fully mature to replace organs, but at tissue level, there is some scope, especially in terms of in vitro testing and stuff. You can grow things specifically in a certain shape and stuff like that. So traditional strategy for uh, tissue engineering that was employed was that you separate samples of stem cells, provide them with growth factors, allow them to multiply. Once they multiply, seed them into a scaffold where proliferation and differentiation into functional tissues. Now, again, differentiation is they start dividing into different types of tissues and become a fully functional tissue. That is the whole concept behind it. So, what is the advantage of 3D bioprinting over here? The primary advantage that I understood was that it adds certain level of automation, consistency, and control in this technique primarily, where precise cell placement, speed control, cell resolution, cell concentration, drop volume are some of the key advantages you get in bioprinting. 3D bioprinting systems can be laser based, inkjet based, or extrusion based, but primarily the ones that I saw were inkjet based 3D printers that were being used in this technology. Okay, so here are a couple of videos just to give you an understanding of how. So that is a 3D model that was made, and that is a again a customized bioprinter. And here you can see a, a tissue sample being prepared, and it is not exactly the way it is actually done. I saw them usually done in this sort of manner, in a scaffold type manner, but I think they did it for demonstrational purposes. Again, Hassan would elaborate this upon his next session, because this is a continuing session where we will go into bioprinting and implants in the next session. So it will be continuing to that point.
Aspect's
So
proprietary lab on a
again,
printer
just a couple of
platform
visual
is one
aids
of the
to
most
just give you a
advanced
basic
tissue engineering
understanding of how they're
technologies in the
using it.
world,
Again, drop, you can
capable
see
of
the
rapidly
liquid
3D
flowing
printing
inside
human
it.
cells
That is your
with
tissue.
biological scaffold.
Here is this was done in 2019. I think the article was published in 2018 or something. They tried to mimic the heart tissue. The basic complexity is that mimicking vascular structures and exact sort of tissue configuration, doing that, mimicking the heart is very difficult. And speed is another factor that comes in play. So the people who did this, they actually said that printing like 1,000 cells a minute would give would they would have to spend 1,000 years printing 1,000 cells a minute to get organ printed, and they need some level of precision. The precision they get is usually in that domain, so it is not viable at this time to print a whole organ that has complex structures in it. It would take too long. Plus, the machines are still being optimized into in that resolution aspect, so they're still a bit behind. Okay, customized drug dosing and drug delivery devices. Okay, I understand the drug industry is very pharmaceutical industry is very big. I'm still a bit not convinced about how effective this technology is in that aspect, but they did mention about customized drug dosing and stuff and how effective. I don't know what big uh, how much the requirement is for customized drug delivery. But they have been working on this, and there are specifically companies over there. Here's a concept they are using for in the using 3D automated technology to make customized drug dosing. So over here, this is a roller that is depositing the drug in powder form, and here is a CNC controlled jet-based system that is adding a fluid on top of it that would make the drug in customized dosing, and which can be they can change it. Each jet can have a different dosage, and they can make multiple dose drugs in the line which can be used later on. Again, I'm not very clear about how effective this technology is in they actually develop this technology. Next is the custom implants. Again, very big domain. 3D printing is definitely the go-to solution for making custom implants, because it is the cheapest way to make something customized. So over here on the left, if you can see, the this lady is using a 3D scanner. Now, 3D scanners have grown a lot in the past couple of years, and they've got these specific for dental, and they've got specific for human body, that you can do a full body scan, leg scans. They've got devices that can go inside your body and they can scan as well inside, and they can use that. So they do the scanning and they make a 3D image out of that. Then they put it into your software, and the software has to refine that image. Definitely, it is not exactly, and there are some abstractions that are made. and definitely it is getting, the more precise the 3D scan is, the less abstraction there is. But they make the design out of it, and then they use that to make parts like these using resin printing, 3 FDM printing, and stuff like that. And then those parts can be used to make molds and stuff for mass production. So here is a video of a custom implant being made. This is dental implant being made. Here are a couple of implants, hip joints, knee joints, and stuff like that. They're definitely used and are functional and can be employed in, but again, they're not cost effective. The mass production based, CNC based made implants or molded implants are still more cost effective at this stage, but customized implants definitely usable. Another thing that I came up was stents and implant stents that I came up with. The picture in the bottom, this is actually pretty old. This is actually Dr. Mirza after you left University of Sheffield. Somebody did this in that period, and I was very surprised that somebody actually 3D printed a whole stent and they actually tested it. This is a drug. This is a what you call it, bioresorbable stent, and they made that and they implanted it in an animal as well, and it actually worked for some reason, and it is actually pretty good as well, but they couldn't refine it further on. There were some limitations later on, so we can have a work up on that as well. Why couldn't they get it done? Okay, these stents are nitinol based, and they actually made these are these have exactly similar properties as laser cut stents, and they've actually tested them mechanically, physically tested, and they've actually tried working out in a way to get them into clinical testing as well. But this is another thing coming up, and we will try to show this more detailed session about this technology that is being used, how they're printing with 3D, uh, printing with nitinol, what type of technology they're using, how it's being done, and whether we can get it here as well and mimic the same sort of thing over here, or we can manipulate our technology in a way that we can get these type of complex designs. We cannot always rely on lasers and stuff. So definitely a perspective over there.